Hi everyone, this is the Aker group, and today we will be presenting our project. Before we dive into the details, let me introduce you to the team. My name is Chi, and my team members are Hosen and Brandon. Let's get started with the basics. What is a system on chip? In recent years, an increasing number of state-of-the-art computer systems have opted for a system on chip, or SoC, architecture. SoCs offer many benefits compared to traditionally structured systems, including reduced power consumption and increased locality between processor and memory units. Typical SoC consists of hardware components such as processors, memory, I/O, and accelerators organized into tiles on a single chip. These tiles may communicate with each other and transfer data through a packet-based multiplane network on chip, or NOC. We will now consider a simplified example of the security risks associated with the traditional SoC architecture. Nowadays, online shopping is an important part of modern life. For example, millions of people use Amazon to do their shopping. Amazon handles all these transactions with lots of processing computers. However, all of these computers are shared between multiple processes. Additionally, all secret information is stored in storage devices that are shared between different processors. As mentioned in the previous slide, an attacker party can control one of these processing units, and then all secret information will be visible to the attacker without any access control system. An access control system adds a layer of security check between every processing unit and storage devices to make sure that only the legally authorized processors can access secret information. In this slide, we will explain one of the simplest security checks that are included in this project. As you can see in this code snippet, a security check function plays the role of a simple access control system. For example, let's assume that a processor wants to access a certain entry in the memory. To do that, it sends a request to the address checking function, which includes 1, its identification number, and 2, the memory address that it needs to access. The address checking function first checks the identification number of the processor to see if it's trusted, and then it checks if the requested memory address is in its statically determined bound. Based on these checks, function will return true or false signal to the processor. True means that it's eligible to access the requested memory address. We have implemented two main functions so far: ACW, or access control wrapper. Each processing unit in the SoC needs one of the access control wrappers. In other words, each ACW manages the request of its processing unit locally. TE, or trusted entity. There is only one TE per SoC. Trusted entity is the manager of the managers, which manages the ACWs to ensure that they work properly. Okay, until now we have talked about the access control itself. As there are a lot of SoCs designed every day, we cannot add access control to them manually. Hence, we implement all our design functions on top of a SoC design platform. ESP is an open source research platform for heterogeneous system on chip design that combines a scalable tile-based architecture and a flexible system-level design methodology. After introducing you to the ESP platform, let's talk about our development workflow. Our workflow can be divided into 3 simple steps. Step 1, create our own hardware accelerator. ESP already provides us with the accelerator generation utility, in which we can configure resources of a custom hardware accelerator on the SoC, such as its inputs and outputs. At this stage, we can also implement our test program, which will access other resources on the SoC. Step 2, using ESP's user interface, we can configure our SoC that will be used for testing later. By default, an SoC consists of one CPU, memory, and I/O tile. Here, we will just have to add our custom hardware accelerator and then generate our custom SoC configuration. Finally, we can run RTL synthesis through Xilinx Vivado. If we have a physical FPGA board that is supported by ESP, we can actually run our SoC with real hardware. But in our case, since we do not have an FPGA board, we will run our SoC simulation within ModelSim instead. To evaluate the correctness and performance of our implementation, we run some of the general purpose benchmarks to measure the performance overhead of the implemented functions of access control system. For the security evaluation, we run some experiments to make sure that the implemented functions work properly. This is the GitHub repository containing our implementation of Aker. Please check it out if you would like to learn more about what we did. Thanks for watching.